We start. Welcome, everyone. Today's seminar is titled Future Directions for Hurricane Research. This talk is going to be given by Dr. Frank Marks, the Director of the Hurricane Research Division, which is part of the Atlantic Oceanographic and Meteorological Laboratory, also known as AOML. As a courtesy to our speaker, please mute your phones and your computers, and we will be recording this seminar. And if you have any questions, we will reserve them to the end. Please include them in the chat. If not, we can unmute your microphones when we get there. So Frank, go ahead and take it away. Thank you.
Thank you, Shirley. Those who don't know me, as Shirley said, meteorologist here at the Atlantic Oceanographic and Meteorological Laboratory. I've been doing hurricane research for over 40 years here at AOML, and I have been directing the Hurricane Research Division since 2003. So today I want to give you a little perspective from my vision of where we need to go for hurricane research in the future. But I want to ground it in what we've accomplished and where we are currently today. So our mission in NOAA for hurricane research is to advance the understanding and prediction of tropical cyclones. Tropical cyclone is a generic term for hurricanes, tropical storms, depressions around the globe. But we want to improve the understanding and prediction of their track, their intensity, structure changes, their impacts utilizing observations, numerical models, and theory. NOAA hurricane research has been going on for over 65 years. So what is our current state of the art? Our operational forecast performance by our hurricane forecast centers at National Hurricane Center and mainly here, but also the Central Pacific Hurricane Center. So this is a plot. On the left is track forecast error by decade, and on the right is the intensity forecast error by decade. And the abscissa is the forecast period out to 5 days. So if you look at the left plot, you see in the decades, we started providing track guidance out to 24 hours in the 50s. When the Hurricane Research Project first started, there was no National Hurricane Center, but they were providing, the Weather Bureau was providing guidance. In the 60s and 70s, and up to the 90s, we were only providing 3 days track forecasts. But since the 2000s, we've been going out to 5 days. And if you look at those plots, what you see is roughly every decade we've gained a day in the morning, or about 24 hours. And that has continued on until the very recent plot, which is 2021. If you look at the intensity on the right, though, you see a slightly different picture. We weren't doing intensity forecasts really until the 70s. That we just didn't have enough understanding of how to do that. I mean, they were provided guidance, but it wasn't very well predicted. And when we talk about intensity, I want to make clear it's the peak wind anywhere in the storm is what the National Hurricane Center calls the tropical cyclone intensity. But what you notice is there was very little improvement until 2009 or so. Starting in 2009, we had a program called the Hurricane Forecast Improvement Program, which was focused on intensity, primarily because we weren't making any progress. But as you can see, since 2009, we've been making good progress. Not quite as good as we have been in track, but we have been really sharpening up our intensity forecast and reducing the errors considerably, almost in half by the time you get to 5 days. So that's kind of where we're at. Now, how did we get there? Well, inside of NOAA, we have many ways that we look at the hurricane or try to characterize its behavior. We have observations on the right. We have aircraft, satellite. We have a number of new probes that go with the ocean. And so we use those observations to improve our models. We have modeling, and then we have analysis, so data assimilation. So we can combine these three pillars, or what I call the support for our understanding and prediction. By combining these different aspects. And I think that's really where the Hurricane Forecast Improvement Project has really allowed us to make the gains we have, both in terms of track and in terms of intensity. The combination of these three things together allow us to evaluate the model performance, to initialize the numerical models, to design better observing strategies that lead to better prediction and therefore better impacts warned or warning for impacts. The Hurricane Forecast Improvement Program that I just mentioned started in 2009 as a unified approach to guide and accelerate our forecast improvements, particularly in intensity. But in 2017, the Weather Act, or the 2017 Weather Forecast Research and Forecasting Improvement Act, suggested to NOAA that you needed to keep the Hurricane Forecast Improvement Program supported and keep accelerating the improvements. And they laid out three specific targets for us: improve the prediction of rapid intensification of the track. Obviously, after having Ian just yesterday go through rapid intensification just before landfall, you understand why that's such an important goal. Improve forecasts of communication of storm hazards, and to incorporate risk communication research to create more effective products. So the way HFIP approached this was we were asked to provide a plan for NOAA focused on these goals, and to lay out the strategies that were needed to achieve these goals. And so those are we have a new strategic plan. If you go to the HFIP website, that's on the right there, you'll get a copy of our strategic plan that was laid out with goals and milestones, clearly laid out for how we were going to get to this, achieve these goals. The other thing about the hurricane intensity and rapid intensity change is the multi-scale nature of the processes. And so we've been challenged, obviously, because of these multi-scale interaction of the different processes, from the vortex scale or the environmental scale, which sets up the structure that the hurricane evolves in. And then we have the vortex itself, and then the thunderstorms or the energy sources for the vortex change. And then, of course, down to the turbulence scales where we live, and what the measurements that we're most interested in is the surface for warning people and alerting them to the hazards that they may experience. So characterizing and understanding these processes and their interactions are a key step in our forecast improvement. And so utilizing our airborne observations, we can provide a unique opportunity to study these processes across all the scales. And so a lot of the new technology and new research that we're doing right now is aimed at trying to focus on these different interactions and to better characterize them, and therefore improve the model's performance in predicting how those processes will affect the storm. So how do we do that? Well, we have our AFEX, or Advancing Prediction of Hurricanes experiment. And this is an extension of a program we started in 2005 called the Intensity Forecasting Experiment. And so we just updated it to, now that we're focusing more on other than intensity, we're adding in the hazards. We wanted to expand the focus of our field program to address a broader spectrum of issues, not just the intensity. So we're collecting, we have three specific goals: to collect observations over a tropical cyclone's life cycle. And so we're actually flying in the aircraft, collecting observations, getting them quality controlled into the ground roughly every 12 hours. And making sure that data gets into the numerical models and gets to the hurricane specialists for their situational awareness. So the AFEX first goal is really an operational focused goal. The second is develop measurement technologies to improve situational awareness. So what are those? What kind of technologies are we talking about? tailed Doppler radar, droplet sounds, the step frequency microwave radiometer, the sail drone, the ocean gliders, the small unmanned aerial systems or UAS. These are all technologies that are being pushed and developed and evaluated. We had a number of them just going on in the past few months of this season, between the sail drones going into a couple of storms, Earl and Fiona. We had gliders operating in both of those storms. We had the small UAS deployed yesterday. The tailed Doppler radar has been operating throughout all these missions on all the NOAA aircraft. We have the satellite observation improvements. We have new AMVs, or atmospheric motion vectors from satellites, a high resolution that we're evaluating. We're looking at new microwave sensors. We have evaluation of small sats, small CubeSats, like the Cygnus experiment and the Tropics experiment. So we're evaluating as many different technologies as we can to improve both situation awareness and then to get that type of data into the numerical models. And finally, improve understanding of physical processes affecting tropical cyclone formation, timing and location of the formation, of genesis of the storm, intensity change and structural change, and the associated hazards. The peak wind is not necessarily directly linked to the hazards. We found that out with the storm surge, and in 2008 we had a major issue with that, where we were using the Saffir-Simpson scale to represent both the hazard from surge and wind, and we noticed that there was a sharp divergence of those warnings in certain situations. So they separated the wind warning from the surge warning. The hazards like the surge and rainfall are not directly related to the wind. You can't have one scale for all. So we need to do a better job of characterizing and understanding the processes that drive these hazards and provide the necessary guidance with the proper uncertainty to assess the risk. So I talked about the NOAA aircraft. These are the platforms that we utilize. On the left is the NOAA P3. We have two of those. Kermit and Miss Piggy are their designations. And then on the right, we have the NOAA G4 aircraft, or Gonzo. And so they fly into the storms. Now, a lot of people might not know how they fly. Here's a typical cross-section of a hurricane. In the height and in space horizontally. So when we fly with the P3s or the Air Force aircraft, we're flying through the bottom of the storms, the lower third of the storm, that typically go up, 10 miles. The G4 will operate up near 45,000 feet at the top of the storm. So they're providing different perspectives, but with the remote sensing tools we have, they give us very similar structure. So what is it like is P3 taking off from Lakeland, Florida, kind of like they were doing this past few weeks, flying into the hurricane. It is a dangerous mission, but we've been doing it for over 60 years, and we have the best crews and the best platforms to operate in. So as we fly, this is a typical mission. This happens to be from Hurricane Dorian. As we fly through the storm, one leg through here, you see what the tail Doppler radar provides us. It gives us a very nice mapping of the wind in 3 dimensions, kind of like a CAT scan of the hurricane. And so we fly these rotated figure 4 or butterfly patterns through the storm to provide a complete mapping. This data is processed directly on the aircraft, quality controlled, and transmitted to the ground via SATCOM, and then directly into the Numerical Model Center. And then the analysis that you see here is also made available to the Hurricane Specialist National Hurricane Center and put right into the AWIP system, their Advanced Weather Information Processing System, that is used for their situation awareness. The other, so in say last season, how many observations do we collect? Well, last season, there were 21 named storms, 7 hurricanes, 4 major hurricanes, 8 landfalls. We flew 467 flight hours, the NOAA aircraft did, in 52 missions. We produced 146 tail Doppler radar analyses. We dropped and processed 1,324 drop signs, 131 airborne expendable bathythermographs to sample the ocean, and 8 Alamo floats that we deployed to sample the upper ocean. Now, these can be combined with many other sensors, but these are kind of the basic observations that we can get from the NOAA aircraft. And so when we come into the model side on the right here, you can see the distribution of these data over each model cycle here on the abscissa of the bar plots. This is every 12 hours. You can see the data cycles and how much of the data gets in. The dark blue is the tail Doppler radar, the G4 TDR is the purple, but you can see they make large amounts of the data other than the satellite obs. And the distribution is shown here on the far right in the plan view, both zoomed in and more larger perspective. So it gives you an idea, and we provide this type of information to hurricane specialists for situation awareness to know what data is getting into the model runs. Because maybe some data didn't get into each model run and they want to, and if there's an issue with the forecast guidance, it's good for them to know what data was available and what was used. And so we produce all this data. It's available on the Atlantic Oceanographic and Meteorological Laboratory, Mellow's website. You can get all the data back into the 90s if you're interested. We also do a lot of work in improving numerical models. The AOML group in NOAA, working with the Environmental Modeling Center up in Washington, that part of the Weather Service, developed the HWARF, or the Hurricane Weather Research and Forecasting System, which is kind of the premier global hurricane forecast tools application. It's run on up to 7 storms anywhere in the globe per 6 hours. It provides high resolution forecast guidance of the hurricane as it evolves. And now we're moving to the next generation hurricane forecast system, which we call the Hurricane Analysis and Forecast System, or HAVS, which is, again, a moving nest, storm-centric, that we're testing right now this season for implementation in 2023 operationally. But our goal is eventually to have this kind of forecast within a global system, say the global FP3. The Hurricane Analysis Forecast System is developed using the same dynamical model core as the global forecast system, which is the global finite volume cube sphere that was developed at the Geophysical Fluid Dynamics Laboratory up in Princeton. And so all of the new modeling systems are taking what they call the unified forecast system approach, taking advantage of that one dynamical core and providing guidance for a full spectrum of forecast products. Emerging research areas that we're really pushing right now is to characterize and understand and predict processes important to the landfall impacts. And so we have been working in collaboration with partners in the university and private sector to collect observations in landfalling situations, where we can gather more information to better characterize the impacts from the storm as it makes landfall. You can imagine the difficulty in getting that coordination because these folks have to move into areas that are being affected by the hurricane and putting up observing systems that can collect data that we can use to better characterize the behavior of the wind, the rain, the storm surge, the severe weather like tornadic events, such as we had, the last couple of days here as Ian came ashore. So we work with them to put towers, portable Doppler radars, surface observation systems that can withstand the hurricane as it comes ashore. A good example here is from last year, the Hurricane Ida, as it came ashore in the Louisiana. We had a number of stations set up to observe what was going on as the storm came ashore. At the same time, we were flying the NOAA aircraft along the coastline and actually up into some of these bays to collect the data we normally collect, the tail delta radar data, and be able to provide data sets that we can look at how the flow and the rain changes as it comes ashore, and to provide better understanding of the processes that affect these hazards as the storm moves inland. So this is a new area of research that we've been doing. It's been going on for quite a number of time, quite a while, but now with the Coastal Act and the requirements upon NOAA, it's taken a much more focused effort, and we're taking advantage of that to collect the observations to help us characterize these hazards. Another emerging research area that's going on within AOML with our partners in the Physical Oceanography Division is we're starting to look at the air-sea interface and the upper ocean. And so we're trying to better characterize how the ocean impacts and evolves as a hurricane goes over. So we have, as I mentioned, all these new tools that we've been taking advantage of. We have the drifters that have been put out in the ocean for decades by Physical Oceanography Division, and the floats that we can deploy in a targeted sense, plus the ocean gliders that have been essential for us, making better measurements of the upper ocean and its evolution, both in salinity and temperature. And then the sail drones, which were added last year, which are autonomous vehicles at the surface that are giving us observations that are terribly unique. And then finally, the drone like we deployed yesterday and the dropsondes that we can deploy. The combination of these different sensors can give us data that we could never get, such as what you're seeing here on the right from the sail drone going through Hurricane Sam. There are two more examples from Fiona and Earl that sail drones intercepted that are providing unparalleled data sets. We could have never gotten the data any other way. And it's going to be invaluable for us to improve not just situation awareness, but model characterization of these processes that drive or fuel or provide energy to the hurricane as it evolves. Other emerging research themes is machine learning. NOAA models, as you can imagine, and these observations provide a tremendous amount of data. And, we haven't been really digesting it as efficiently as we could. And so the addition of these machine learning techniques are going to be essential for us to digest all this new information, as well as the model guidance products, and try to better understand how to take advantage of all these different data sources to better warn and guide people in terms of what they should be doing or what they should expect when a storm approaches. And so we have a couple of examples. We're very much in the nascent part of this development, but I think it's going to accelerate rapidly. There's many groups that have approached us that want to work with us on these type of concepts. New ideas are being thrown out there continuously. There are many approaches to the problem. As you can imagine, this is essential because most of the processes are nonlinear that drive hurricane intensity change. And so, typical statistical regression type models may not be adequate for us to really be able to take advantage of this information. So taking advantage of these new machine learning techniques is going to be critical for us to really continue to accelerate our ability to warn and guide people in terms of these harmful storms. Another emerging area that I think is extremely exciting is this idea of how we improve forecast communication of hazards. This is a linkage between social, behavioral, and economic sciences and physical science, something that is not always something we think about on the meteorological side. We've always been, we're physical scientists, we tend to put out forecast guidance for things we can measure and verify, and not necessarily are as useful as you might think to the public or to our stakeholders. So we've been starting through the last few disaster supplementals, we've been pushing the idea of funding and supporting research groups in the social, behavioral, and economic sciences to work with us on looking at our products and trying to help us assess how much of that information is being used, how it's being used, is it useful, and how can we improve the products we have that provide this guidance to make them more effective. So I'm just highlighting 4 of the projects here. One where we've been looking at what they call minding the gap. We just did a study this past storm where we start 2 or 3 days before the storm approaches. We start sending out surveys to sample what our partners are doing. That's how it's changing. So we're looking at that. Minding the gap is evaluating how our products are used by our core partners. And are they, seeing the differences as storms evolve? And how do we communicate and optimizing the information? So a lot of these projects are just coming to their conclusion. Castle Williamsburg gave a great seminar to HFIP, and we're probably going to have one at the big annual meeting in November, where we're trying to coordinate, or what Castle calls triangulation, where we take these projects and we look at overlapping themes and takeaways that come out of these different efforts. So Castle and the group up in OAR headquarters working on the social behavioral sciences are really starting to take a look at and how we combine this information to better provide risk guidance to our key partners and the public. I think this is just an exciting area of new research. Okay, so future research. Okay, so you hear what we've done, you hear what we're doing right now to the new projects. I want to talk a little bit about what my vision of where we need to go. And I think part of this is driven by climate change. I mean, I don't know how many stories I've seen today that say, oh, well, Ian is just a product of climate change. That, the waters are getting warmer and therefore storms are getting stronger. That is all true. If you look at the climate resilience TCs, though, that I think is a much more local problem. The climate discussion of hurricanes so far has been very much from a basin or a global perspective and not a regional perspective. Hurricanes are one of the largest of the billion-dollar disasters. If you go to the NOAA website, the billion-dollar disaster website, you look every year, hurricanes are usually a dominant form of the billion, making up a not large number of the billion-dollar disasters. For example, 2021, there were $80.2 billion damage caused by hurricanes making landfall. It's a obvious target for people to talk about changes in climate. But I think one of the things that's overlooked is that climate change is a local issue as well. Hurricanes might not be a major problem for New England or California. That remains to be seen, but it's definitely a major climate resiliency issue for Miami and for New Orleans. What we expect, we're used to hurricanes down here, more so than, say, New York. But it's really how they are changing relative to our perspective that is critical. And so I think there's a lot of room for us to take advantage of this need in our future research. Uh, our goal is to improve risk communication. We already have observations, modeling, and analysis providing guidance products, but we're missing one piece, that social behavioral economic science section. And I think that we need to embrace and take advantage of that to help us focus our technology and our expertise on a problem that is going to be a massive problem for the U.S. stakeholders, the public, and that is climate resiliency. How do we make ourselves climate resilient? And to bring that home a little bit, I'll talk a little bit about tropical cyclone risk. If you go to this $1 billion website and you look at the areas where we've had the biggest hurricane losses, Texas, Louisiana, Florida, Puerto Rico, the southeast coast. And then if you go down into total direct damages and you look at the locations where the damage is the worst in terms of percentage GDP, it even sharpens it up more to the areas that we're seeing the biggest damage. So that the tropical cyclone risk is a local issue. It is not a global, it's a global issue, obviously, but what is going to happen locally? And I think that's where the future research, hurricane research, needs to take advantage of what we've done so far to move to the next step. Part of the issue is, I think we're convoluting a little bit what the real risk is. This is looking at hurricane events and hurricane costs per year on average over the last 4 decades. The blue is the number of events per year, roughly 1 to 1.5 events, over those decades. That hasn't changed that much. The number of landfalling events has, on average, over those 4 decades, has not changed. What has changed is the cost per year. It's going up by a factor of 2 or 3 every decade. And part of that is not the hurricane occurrence, but the way we live. And so this hammers home the fact that this is a local issue. And it's a political issue, not just a social behavioral science issue. And so we need to be doing research to better inform decision makers, state, local governments, national too, obviously. But ones in these hurricane-prone regions need to know how to best mitigate this disaster increase in cost. A lot of it has to do with where people want to live, demographic shifts in population, building, going back and putting buildings back in hurricane-prone regions. A big issue, I think, for the U.S. government is going to be flood insurance. Major disasters like Hurricane Ian caused huge flood losses, which the U.S. government underwrites. So this is a major area I think that we need to focus on in the future. And my recommendations there is I think we need to develop these interdisciplinary partnerships and collaborations. We need to focus on local and regional climate adaptation resiliency. A good example, University of Miami just formed their Resiliency Academy to start looking at the South Florida resilience to climate stress and impacts. FIU International Hurricane Research Center, we've been partnering with them for over 20 years since Hurricane Andrew on hazard modeling for driving our insurance. These are the type of partnerships I think that we have to engage and become a partner with as we develop our future hurricane research. We need to bring our physical science research expertise to bear on issues related to resiliency. And so I think this is where I think we need to go. I think the stakeholder needs climate risk assessment and resiliency. We have the ability to do storm scale high resolution reanalysis within a global reanalysis. We have global reanalysis, but we don't have hurricane reanalysis. We need to look at storm surge and inland flooding uncertainty how that impacts catastrophe risk models, insurance and reinsurance. AOML was partially partnering with FIU to develop the wind hazard model for the state of Florida CAT model. That is the type of thing I think we need to do more of. We need to engage more in those type of things and bring our expertise to bear. Expertise in S2S research and guidance, seasonal to subseasonal. We've been involved with developing guidance products for tornadoes and for hurricanes on the seasonal to subseasonal scale. So we have some expertise there. We have expertise in both data science and modeling and data simulation. We have high resolution modeling and DA system expertise in AOML and in NOAA that we need to bring to bear on this. We have data. We have over 40 years of field program data in hurricanes. We have ocean and satellite observations. To me, this is a huge opportunity for us to expand our capacity in our research to address a key problem that's going to drive our country and the globe crazy over the next decade, century, decades and centuries. And so that's where I think we need to be moving and where I think our goals need to be set to take what we've learned from the HFIP and the AFEX and apply that towards the climate resiliency issue. And with that, I'm going to stop and take questions. And I thank you for your attention.
Thank you, Frank, for that very illuminative talk of hearing of the future of hurricane research. We've got a couple of comments and questions here, and if anyone has additional comments, please put those in the chat box. So we'll start with the first one from Daniel Melendez. Early on, he mentioned, what has been the scientific impact of the mobile short-wave radars with regards to processes in tropical cyclones?
That's a good question, Daniel. So far, those data sets have been invaluable for helping us better understand how a storm changes as it comes ashore. The data is not getting in, those mobile radar data sets are not getting into the numerical models as of yet. We had a project plan we put together to fund that, but it didn't get funded. It just didn't make the cut. But that's a goal that the providers of these mobile radars have set. Still, the WSR 88Ds, the Weather Service Radar 88. Sorry, I think I got muted. The most useful data right now getting into numerical models from Doppler radars is from the WSR 88Ds, not from the mobile platforms. The mobile platforms are potentially a useful product, but they're mainly used for looking at what happened after the fact.
Thank you, Frank. There's another question when you were showing the information from the NCDC billions page. Rob asked didn't Pilkey and Lancy do a study on some of the stuff that was shown on that? And do we have any information on some of those?
Correct. Yes. Roger Pilkey Jr. and Chris Lancy and collaborators had, for each decade, they've done 3 of these assessments showing that exactly what I was pointing out, Rob, that each decade the cost has gone up much more than the number of events have gone up. There's a very large difference between the number of events and the impacts. And Roger and Chris clearly stated that, part of it, they adjusted for everything like cost of living and how the dollar or our economy has changed. And so all those costs that I showed in the $1 billion page are adjusted to the same year. And so these events have blown up in terms of what the costs are because of the way the population has changed, the way we build, where we build, the type of infrastructure we have, and where we put that infrastructure, particularly in hurricane-prone areas. And that's why I think this idea of climate resiliency is an important one, because it is a local issue. We have to stop talking about the global number of cyclones and their energy and all that. We have to get down to the nitty gritty of what it's doing to the local communities and how they react and how they prepare. Uh, are we building our sewer systems or our water treatment systems appropriately to deal with these things? We know already that on Miami Beach, they're, spending a lot of money to put in pumps, kind of like they have in New Orleans. I mean, those are mitigation issues, but are they going to be effective? Do we have the information they need to characterize what the impacts might be? No, I don't think so. We need to do that.
Thank you. There's another question here. Are we fully leveraging research capabilities within federal private enterprise?
I think we're doing a better job. One of the things I would say from my experience with the Hurricane Forecast Improvement Program was when we started, we had diverse parts of NOAA looking at the hurricane problem and talking about different needs. What the Hurricane Forecast Improvement Program, in my mind, did was focus our efforts on the operational goal. What was the National Hurricane Center, the Central Pacific Hurricane Center, the National Weather Service highest priority goals for hurricanes? Was it track? Was it intensity? Was it rainfall? What was it? Give us those goals. We used those goals and we laid out a plan directly to address those goals. And so to me, that has been the most important aspect of leveraging our resources. We had done that already with the field program, the IFEX experiment that was put together in 2005. We unified our operational and research needs into one picture that we could use to justify going and flying in the storms. That's a very costly endeavor. And to justify that and to justify the cost for the aircraft, you had to do something like that. We did the same thing now with the forecasting through HFIP. What I think we need to do is take advantage of that unification and focus in HFIP that we're now driving towards the goals that the Weather Act gave us, but now come up with new goals that deal with climate resiliency for tropical cyclones. That would be my recommendation as we move forward. And I think what you do is you fold in more and more of the NOAA capabilities into solving a problem that's going to be a major one as we move forward.
All right. I believe Stan Goldenberg had his hand up, but he may have put his question in the chat, so I will.
Well, I can do it better verbally if you let me, or you want to read it from the chat.
Go ahead, Stan.
Yeah, I just would urge you to be very careful with your statements because of all the media blitz on this, trying to attribute this from man-made climate change, like the ridiculous interview with Don Lemon and Jamie yesterday or the day before. But what are you made a statement. You said, yeah, hurricanes are getting stronger because SSTs are getting warmer due to climate change.
I did not say that statement. I said that is a statement that we hear.
Okay, it sounded like you were agreeing with it. Thank you. I just want to clarify that because those of us who have studied it, like Chris Lancey and myself, see no evidence of that at this time. Go ahead.
Stan, I don't have a say in that. I'm not a climate expert. I think we do have people that have expertise in science, subseasonal to seasonal forecasting, and I think we need to take advantage of those folks.
And I'm one of those people. That's why I spoke up. So go ahead.
Thank you. There's another question from Gustavo Goni. He says, I understand that for associated hazards, you meant rainfall, coastal inundation, tornadoes, etc. Is there a similar plot like the one you showed for track and intensity for these hazards, showing how their forecasts have been improved or not?
That's a great question, Gustavo, and it's one that I think we've been struggling with for HFIP. trying to get a characterization of those. First of all, the products that we have only been unified under the Hurricane Center probably since the last 10 years. So the way part of the product development that's an issue, Gustavo, is there's the National Hurricane Center is responsible for the hurricane forecast. The Weather Prediction Center provides the rainfall, what they call quantitative precipitation forecast guidance. And then the Severe Storms Prediction Center in Norman provides the tornado warning. The Hurricane Center does track, intensity, and surge. So there's a little bit of a dichotomy of the products. But one of the things we've been trying to do as we move into this new area of looking at the hazards is try and build a framework by which we can look at all these hazards. The Weather Service is unifying that under what they call hazard services, but that's for everything nationally, not just for hurricane. So we have come up with a strategy that's called the Forecasting a Continuum of Environmental Threats, called FACETS. It was started under the Severe Weather program out in Norman, but it addresses how do we break down this idea of warning for a hazard every 6 hours when they're a continuum of threats, and with that we can't just look at everything every 6 hours. Now, the other part of that, though, is the use of social, behavioral, and economic sciences to evaluate the products before you make them operational. And so, Gustavo, to your point, we don't have currently a way to track that. We have kind of a national track and not so much a hurricane-specific track for those hazards. So that's something that needs to be developed. That's a good question, Gustavo, and it's something we need.
All right, we've got a couple more questions here for you, Frank. Would it be useful to openly provide observations and model output that are fair, compliant, and analysis ready? How would any citizen would search and find the data and information they seek?
Okay, so first of all of our experimental products are on the web and available. I don't know how many people showed the different products that are available. Pretty much anything hurricane research develops and puts out online finds its way to people somehow. There are numerous sites where you can get the data. My recommendation is to go to the NOAA sites, the Environmental Modeling Center. HFIP provides a number of links to go to the HFIP website to where you can get that model data. In terms of observations, we try and keep up with those at the Atlantic Oceanographic Meteorological Laboratory for the aircraft observations. The satellite data NESDIS provides all the time. So there are many, many places that the public or interested researchers can get access to the data. And my recommendation, though, is contact your NOAA partners if you're interested in that. And if there's an interest in that, maybe we should add that to our frequently asked questions. I'm not sure if that's already on the AOML website as a frequently asked question, but it should be if it's not.
All right, we have a couple more minutes here. I'm going to final a couple more questions as well. Can you expand more upon the future research needs for hurricane modeling?
Okay. Well, the hurricane models have improved dramatically, I'd say, in the last 10 years. There's been more of a unified focus on taking advantage of all the observations and using those observations to improve the model guidance. I think the biggest area I would say is dealing with the uncertainty. No numerical model provides a perfect forecast. The Hurricane Center and the operational centers use what they call consensus. They take an ensemble of either different models or the same model, and they look at how those models evolve in time and how much they're different as they evolve in determining uncertainty of a certain part, aspect, or characterization of the hurricane itself. So in my mind, the focus has to be taking advantage of these ensembles or consensus of these different types of models. Some of the behavior is going to be linear and can be dealt with in a statistical linear regression type of way, but a lot of these hazards are nonlinear. And therefore, that's where I think taking advantage of the ensembles with the machine learning and combining the observations and the model data together is going to be a place that we have to put a lot of our emphasis. But in terms of the modeling, I would say improving, right now we're working to improve the observation use, but I think the next step is getting the uncertainty addressed and how we can take advantage of that uncertainty to improve the product guidance.
And one last question here for you, Frank. Intensity forecast accuracy is close to reach the predictability limit in our current framework. Do you have any thoughts to reframe our intensity forecast future?
I would say don't play with it because that's not the hazard. I think what we need to do is focus on the hazard. People, it's always going to be, oh, just give me a number, Cat 5, Cat 4. My question is, what's the difference between Cat 4 and Cat 5? And they look at me strange. And I say, it's only 1 mile an hour. Was Ian a Cat 4 or a Cat 5? Well, our uncertainty of even measuring what Ian was varies depending on what type of instrument you got. And so, I think intensity is a little bit of a red herring in terms of forecast guidance for landfall events. Out at sea, it's fine. You want to characterize the storm out at sea. If you're not in a ship and you're not worried about the waves or the winds, maybe a single number is okay. I would say that we need to do more with the structure. We know that hazards like surge are not only dependent on the peak wind, they're dependent on the structure of the wind field. And I think people have to understand that hurricanes evolve. They're like human beings. They start out skinny and small, and then they get big and fat, and then, they decay. So they go through their life cycle and they change as they go. And so I think, having one number that's a peak wind is the minimalist categorization we can give for the intensity of the storm. I would much rather see us not worry so much about the intensity and the intensity limit, but start focusing on uncertainty and structure.
All right, thank you, Frank. Thank you for that wonderful presentation and the dialogue that we've had here. I don't see any other pressing questions, just comments here and there. So with a little bit of time here, we will go ahead and close. Again, thank you again for joining us for this AOML Science Seminar Series. The seminar is being recorded and will be available on AOML's YouTube channel in the coming days. Thank you again and have a wonderful day.
Thank you all.